In the last video, we have seen the problem of 13.8 where we have found all these production cost for these stages, 4 stages we have calculated, and here we have considered 4 combinations because here the condition was at unit 1 and 2 as must run unit. That means we need to actually run unit 1 and 2 all the time. If you see, actually all these combination have unit 1 and 2 running, and that is because if you actually notice the combination table or combination chart, here you will find that only these 4 combination have unit 1 and 2 running. All the other combination you will find that one will be actually turned off or both the unit will be turned off. So that is why we are only taking this x1, x2, x3 and x9. Only these 4 combination have 1 and 2 running. Otherwise, if the condition of that question was different, we would actually take other combinations too in this consideration. So that is how we have actually calculated all these values for production cost for these 4 stages, as there are 2 stages similar, so that is why we counted 4 among these 6 stages. And now in the next problem 13.9, here you can see that the generating unit startup and shutdown cost here as $3K and $1.5K, and here you can see that unit 1 and 2 in the final stage will be must run. That means that in the first and last stage the unit is fixed. There will be only x9 combination, but on the other stages there are possible cases or possible combinations are more than one. So that is why we need to actually calculate the cost and find out the minimum cost among these combination. So that means from first stage to second stage, if we want to go, which combination will be more optimum. So that is why we will actually calculate all these values with the help of the previous math also that we have already done, and then we will find this find the value with the help of these equations. You can find the equation in the book, and we will be using backward dynamic programming. And there are 2 methods actually, forward and backward dynamic programming. We will be using backward dynamic programming, and the reason is you can see that both the approach will actually give the same result if the initial and the final stage have the same load. And you know that we have that actually same result for same load for our initial and final stage, 1100 megawatt. And here you can actually see backward dynamic programming is more suitable, as you can read from here. So that is why we are going to use the backward dynamic programming, but you will get the same result if you use forward dynamic programming. Only the equations will be a bit different. You can follow that too. There are actually 6 stages, but we have calculated the values for 4 stages in the previous code because we actually need them in this math, not in the previous one. And here you can see T is the transition cost, and this cost is for actually moving from one combination to another combination, and F is the previous stage's cost, and P is the cost of this stage. And here we are actually calculating for all the combination, and then we will find the minimum from them, and that minimum will be actually the main cost. And here you can see the minimum function is actually mainly finding the minimum values from all these combinations, and whichever will be minimum, that we will actually accept, and we will not use the other combinations. And then we will actually write the combination for all these stages. For 6 stages we will find 6 optimum path, and by following them we can get the total cost will be the minimum, the lowest cost we will get from this system. And here you can see that the last stage here, and this is the first stage, we need to actually follow this path. You can see the bold line here is the minimum cost path, and here we will find this transition cost too for this path by seeing how many unit we need to turn on or shut down. And here you can see that in this combination here we have found our cost value. If you actually check with our output that we have actually calculated 45,844, but if you actually notice in this table you will see that this value is not exactly same. The value will be a bit different, and that is why our total calculated cost will be a bit different from this book, and that is why the resultant path or the following path that will be the optimum will be a bit different from the book, because the calculation here the calculated output from our PC is actually a bit different from their output. and that can happen due to the precision value that we have actually taken, or because we have used the roundup value, and that is why you will see that combination will be a bit different. Here you can see that in the x1 all four unit is turned on, and if we want to go from x1 to x2, there we need to actually turn off one unit, and there in x3 also we need to turn off one unit, and if we want to go x9, then we need to turn off 2 unit. And we know that if we want to actually turn off 1 unit, we need to actually give the cost as 1.5k. And here you can see from x3 to x9 this is 1.5k, and here to 1.5k, but in from x1 to x9 there are 2 unit we need to turn off, and that is why this is a 3k dollar. You can see here in the x9 combination, if you see for 1100, here you can see both the 3 and 4 unit is turned off, and for x1 all 4 is turned on, so we need to turn off 2 unit for the last stage. And here you can see all the values after calculating the cost. I hope you understand this, how this transition costs are calculated. And then here we just need to put these values here in the transition cost, and the previous cost, previous stages cost, and here then the total P, that will be actually from the value of the table. And after putting all this value, after summing them up, we will get the total value, and then we will find the minimum. As this was our stage 5, we used F will be the last stage's value, and then all these transition costs that we just saw previously, and then all the value from our table for this 3 combination. And this was our stage 5. If you go to stage 5, that was actually for 400 megawatt. You can actually match them up if you want. We are getting 58,000 something, 59,000 something, and 58,000 something again. And if you see, these values are this one, the P. In this equation, the P will be that values. So I hope you understood which value is actually we are getting from which position, or what we actually need to put in those equation. And now we will just write our code. So let's go there, and after the value we have calculated this part in the previous section. So today here we need to create another array that will be unit commit, and then z comma j will be equal to total cost. And now after this we will take m, so here we are just getting all the values from the first row and multiplying them with m, our new matrix. You can see the value, and after that again unit commitment for the last stage. Again we need to multiply them. We are doing this because in the question we have actually written that the first and the last stage will have the x9 combination. That means in the first and last stage only the first and second unit will turn on, and that is actually inside our x9 combination. That is why we made this m matrix, and we are actually multiplying the values of first row and the last row. Okay, now you can actually check the value here, our unit commit matrix value. Here you can see the change step by step, what is actually happening here. All these values in the first stage and in the last stage, only these two value will remain. This is actually the value of x9 combination. If you actually match it, you can see from the table too. Here you will see the value, that is actually this one. The total cost is actually showing here, and for the first and last stage we are actually making them all the value equal to 0, and only the x9 combination value will remain. So after doing this, here for all the row, and column number will be 6, we need to do this again. Before that, we need to actually initialize the matrix AA. AA will look like this: 4 row and 6 column. And then after this, for all the 4 row, for number of sixth column, unit commitment for number of 6 row and all the column. This is the condition you can see. For this one, we are actually putting them inside this new array or matrix. Then after this, we will run another for loop here that will run for 5 times from 5 till 1, and it will be decremented decremented by 1 each time the for loop runs. And after this, we will take a variable count will be equal to 0, temporary will be equal to 0, and then another for loop for 4 times. If AA, then for k I plus 1, this value is greater than 0, then unit commitment, okay, and unit commitment I comma j is greater than 0. That means both the matrix will have to actually be 0 at the same time. Then we will do this. Okay, we will check this one later. I'm just writing this for checking purpose. You don't need to write that line. And then if this happens, then we will actually increment the value of count, and here in the temporary we will use this count variable in this temporary temporary array. We will write the equation here. The value from the unit commit matrix and then transition cost. The value from the unit commit matrix is the production cost that we have calculated previously, and after this the transition cost that will be calculated. We need to actually give the transition cost here. Okay, I have actually written all these values, taken all these values and written it inside that array. You can actually find all these values in this image. And after this, here the value from the AA, this is actually the value of previous stage, right? Like actually we have seen in our book, the exactly same equation. You just need to write it in your own way, and then this one will be equal to k. Here we are taking another variable m. Previously we have taken m as our matrix, but now we don't need that matrix, so we are actually using that m for another variable. And after this we will write our find the path, and here let's use j and I. If ij is not equal 0, and if it is less than m, then m will be this value, and then we will write it inside another array called combination. Okay, let me see, we have used a com for our combination, so we will just write full combination here as a new array. We cannot use the same one. And after this, else condition, m will be equal m if it is not greater than the value of m. Okay, and after this we can show this value. Okay, we can see the value of n here, and now let's display the path. And we will show the path by writing the name of the combination. So here, if combination of I will be equal to 1, we will display x1. So x1 will be the minimum path. We have already calculated all the minimum values. Now we are just writing the path. Okay, and here if it is 2, then we will write x2, and if it is 3, then we will write x3, and if it is 4, then we will write x9. Okay, so we have this 4 combination, but there are 6 stage. Okay, we are getting some error here. We're getting the value of n properly, but not the path. Let me check again. Let's just see how the unit commit looks like. Okay, there are actually 4 rows here. We need to have 6 rows as we have 6 stages. Okay, in the we actually wrote the code in the previous with the previous code, and here there we used 4 stages only. We have actually ignored the other 2 stages as they have the similar value, but for calculating the unit commitment we need to consider all of them, so we need to write these last stages also here, and z will be equal to from 1 to 6 for 6 stages. Okay, now we need to actually show the output. Okay, let's run it again. Okay, this time we are getting all the path here. You can see the values, and here we are actually getting the value of this matrix, and this is the actually main thing where we are calculating if the path is actually showing correctly or not. We can actually analyze these values by rearranging them in an Word document. Let me just show you here by putting the values inside a table. Okay, let me create a table first. There were 4 row and 6 column. So 4 row and 6 column. Now I will just enter all these values. Okay, and here I have written the values here properly, and then in the right side I have written the combination so you can understand properly, and I will write the answer here. You can see from the first stage to the second stage, if you see the x1 combination is actually the lowest, has the lowest cost, so we will go from x9 to x1, and then from there in the third stage, if you notice, we have the minimum value in the x1 combination again. So again we will write x1, and from the third stage to fourth stage, if we want to go, again x1 is the minimum cost, x1 has the minimum cost, so again we will go from x1 to x1. If we go from the fourth to fifth stage, you can see that x3 is the minimum, and again if we go to the fifth to sixth stage, and then we will find x9 is the only combination there. So here is the path, and here is our output. You can see the exactly same output we are getting from this one.